Good afternoon, everyone. Sorry for a little bit waiting, trying to set it up. I think it's all set now. So my name is Vishal Verma. I am performance engineer at Intel, working in performance on storage systems for more than 5 years now. My partner Tushar, unfortunately, he couldn't make it, and I'll be covering for him as well in this talk. So I'm going to talk about some workload analysis of key-value stores on non-volatile media, which is Intel new generation 3D NAND, which I'll talk in detail, but that's the topic here. And so the outline, working in this performance for more than 5 years on this storage systems, we look at the key value stores, which is important, and we're looking at characterizing performance of key value stores and looking at the behavior and establish some best known practices in order to, characterize the performance out of key value stores. So in the outline says the key value store, what and why are they important, what are the data structures of key value stores, and then some design choices if somebody would like to, depending on the application, what key value store someone would choose, and some trade-offs in terms of performance, or it's a space and write amplification. So we'll talk about those parameters. And then there would be some performance testing work we did on Intel's 3D NAND. How do they compare different key value stores? So I'll talk about that. Okay. So first of all, what are the key value stores? Traditionally, if we look at in today's world, the storage is growing over and over, and it seems like a lot of the data is unstructured. What happens is there is this data growth is large, and the traditional databases, they are designed for where there is a predefined mechanisms, like a predefined schema involved with organizing the data in relational databases. And in today's world, what happens is data is unstructured. There are a lot of random reads and random write IOs happening with these relational database or whatever database we use. So key value store is an alternative. They have this. They brings in flexibility to an application, because the application has full control over what gets stored in the value. So they are simple, and there's no SQL database. So like in a traditional relational database, there is a query. You have to have certain type, whether you want to query or like insert. But in this case, all you have is like you have some common defined API operations like get, put, delete. All your application, it talks directly to the data based on key and value. So there is whatever value gets stored, there is a key associated with it, which is a unique identifier regarding how do you access your value. It's based on your key, which is unique. So in this example here, we are showing a phone directory. Like it's a very basic example where you have your phone numbers as values, and based on your index on the name, right? So based on your name, you can actually refer to a value, which is a key here depicted. So what are the benefits using key value stores? Since there is no enforcement of any structure to the data, you look at performance, like it's highly scalable and highly performant based, because there is no application has a flexibility, there is no structure or any data, and it provides a low TCO. Simplify operations whenever you in a data center you want to add or remove capacity. There is this cost, like total cost of ownership, which is reduced with using key value stores. We'll look at in detail how what do I mean by that? So with the next, so that was just an intro to KeyValue Stores. Okay, what are them? Why are they important? And then what are the design choices and different trade-offs when we talk about KeyValue Stores? So we'll start with the traditional B-Tree. So right in this diagram, we're showing internal nodes, which are shaded green, which are pivot keys. And then there are leaf nodes, which actually stores the data, which in this case, like a key value pair. And as you can see, there is a root node right at the top. Any value which is less than that value, it goes left. Any value on the right is greater than that. So that's a balanced tree when we call Btree. It has an inherent property of being balanced. So the first thing which comes to the data structure, okay, what is my query? How fast, like what is the time complexity of my queries, and how good is insertion and deletion? So theoretically, if you look at with a tree, there is a height associated with a tree, which is the distance from my root node to the leaf node. What's the distance? So in this case, it's shown like the height of the tree is 2. So query time, right? How much is it? What is the time complexity? So it's shown it's logarithmic in nature. Logarithmic time, which is pretty fast for a query. Like if you want to do a read IO using a B-Tree, the search time are pretty in the logarithmic complexity. But what about the insertions, right? So for insertion and deletion, because the tree gets rebalanced, there is splitting involved when the node gets, like this leaf gets full, then the tree would split itself to rebalance itself, and that involves a write amplification, what we say read and write amplification. Whenever you want to insert data, it has to basically read all the nodes until it finds that okay, where to insert the value. And all those read and write IOs, which happens before the actual data gets written, there is a lot of amplification happening. And of course, the space fragmentation. When the full leaf nodes are split, for instance, my node size is like 4K, and I want to insert another value, and the leaf is full, then you would actually, you split it, you divide by your page-aligned IO size, and you are actually wasting your space because you're splitting it in whatever chunk size or like block size you have for the leaf, and so you're splitting it, and the space gets wasted. What are the common DB engines which use Btree? It's traditional. I mean, there are a lot of them: Berkeley DB, MySQL InnoDB. There's a WireTiger, and what are the common? What workloads are actually beneficial when using Btree? So read-intensive workload, definitely, because the search time is all logarithmic in nature, so you have pretty fast read performance. But for it also involves read and write and space amplification. That's with Btrees. And what about the write, right? So whenever there is a byte size update, it has to be on a page-aligned IO basis, what I was saying. So a single byte size end up in a page size read or write, and that involves a lot of space amplification. And if you have for instance, if you have a 16K block size, right, and if your data is like 10K, and you are spending time in compressing it, and it turns out to be like a 5K, for example, after compression, you compressed it, but even though you compressed it, it will still be, stored in those block sizes, because that's the minimal block size it uses, which is good for storing the data on the disk, because larger the block size, the more, higher performance you get. But we are looking at the fragmentation piece here, which is a lot, which adds a lot of amplification. So those were just the theory terms, right? What the B-Tree is, how the read amplification, write amplification is. But then we ended up, we wanted to do some performance testing in order to understand how does it behave really in the real world, and especially on the non-volatile media, which Intel has a next generation 3D NAND and 3D crosspoint. So we took a 3D NAND, Intel P4500, which is a 4 terabyte, which shows a data set which is greater than the memory, so that it actually does, the disk IOs. And it's a common practice to have, the ratio of your so we chose like 3:1 DRAM size, where, your data is not fitting in the memory, because our memory was, if you look at the configs, 64 gig memory, 500 gig data set, so it will get stored in your non-volatile media, and we'll see how it behaves when it does IOs, read and write. So we chose a KeyValue database, the benchmark called dbbench. It has, it's a synthetic benchmark where you can run some workloads and look at how my read and write performance underneath of my database is actually performing. So we ran 30-minute tests to see how the performance behaves. So one of the workload which is brought up, we have seen a lot in the KeyValue Store and in the dbbench, like the ReadWrite. It's a typical workload which involves single writer thread, and there are n number of readers which are doing point queries to the database. So we ran this workload across 500 million rows. So this is like a 16-byte keys and 1,000-byte value, and 500 million rows correspond to approximately 500 gig of data. And if you look at this graph, this is showing write and read IOPS, ops per second. So write IOPS are like one thread which is writing, how fast is it writing, and then the reads are like, the graph is showing one thread, how fast or how slow it was, and then over time. And so the 30-minute run, x-axis is showing row count, which is like 5,000 ops. So every 5,000 ops, we get a data point. So across 30 minutes, this is like how many operations we did and how did it perform over time. The main thing we were looking at was how fast the write performance was and how fast was the read. So 2.15 million operations were completed from a single write thread, and then the reads were pretty fast. So that it just tell us that the read performance tend to be pretty good with using the B-trees. And this shows just this graph is just talking about the latency seconds per op for every operation it completed running dbbench. So this was a gist of B-tree. Now the next one we'll talk about is LSM. There are more performance charts we'll talk about later on, which will compare these three different key-value stores. So let's see the LSM trees. It's a log structured merge tree. They are fast. They actually transform your random writes into few sequential writes. And how does it do that? There is a write ahead log. It's basically append only journal. So every write comes in, it just starts appending it. And it uses an in-memory store which allows inexpensive writes going to the memory. So a typical LSM is like level based, where you have your level 0, they call it, which is based on the memory store, and subsequent other levels are stored on the disk. So It uses in-memory store. It's inexpensive writes, and it's flushed sequentially to the first level in persistent store. So these mechanisms allow it to basically have really high write performance with the LSM tree. There is a compaction activity which happens in the background just to trim duplicate entries, and it involves read and write amplification because it has to read, merge, and then for sorting the data. So there is a lot of activities which happen in the background, which incurs write amplification and read amplification. But anyways, for the LSM tree, what are the different DB engines in production which use LSM tree? So first one, the most common one, RocksDB, used by Facebook for MyRocks engine or MySQL, and there is a WireTiger, Cassandra, LevelDB. So all these engines use LSM tree in production. We have a operation, how it behaves, how LSM tree works. So this is an example of NLevel merge tree. It's basically transforming random writes sequential using a write-ahead log. So every write, as I was telling you, it happens to be in the mem store in your memory. So this is like a buffered. It gets buffered in the memory, and once the buffers are full, it gets flushed into your subsequent levels, which are stored in the persistent store, which would be C1, CN, C1, C2. So these are all stored in your persistent store. And C0 in this picture is showing in memory, which is every write comes to the memory, and it's pretty fast. So it's optimized for insertion by buffering, and then they support faster lookups because there is I was talking about compaction, which sorts the keys and keys in the background, and that actually helps with the lookups, faster lookups. So the design choice of LSM tree, these are append-only constructs. There is no read, modify, and write kind of mechanism. It reduces fragmentation because there is nothing like a page-aligned I/O, like in case of Btree, where you have to have, if your data size is less than your page-aligned, like page size, there is nothing where, in LSM case, there is no fragmentation because you are not doing any page-aligned IOs here. So reads, these are there's a compaction happening, and then it has to scan all the levels. So what happens is for reads there is a point query and then there's a range query. So in case of a range query, you have to basically walk through all the levels to get a key, and that involves a lot of read operations, which translate to read amplification happening in the LSM tree. RocksDB, as we saw, it uses LSM. They use a concept of Bloom filters, which to optimize the read operations for specifically for point queries, which helps the read performance. Then there are delete operations, which is called like deferred deletes via tombstone. So tombstone files, it keeps track of it, and they don't disappear until actually the compaction process kicks in and starts, merging your values. And that's when this tombstone get deleted. So they are deferred deletes, but when they disappear is using the compaction process. And then there is a read amplification and space amplification. So read amplification is depending on your number of levels. It can be one, okay, my key was just in my L0, or it can be as many as it has to go through all the levels to get the key. So it really depends. And then there is a write amplification, where this is taken from a common LSM summary. 1 + 1 + fan out is the is the call for the write amp. So it's suited for write intensive workloads, LSM trees. They have better compression. There is no page-aligned IOs like we saw in the B-trees. And they have lower write and space amplification compared to B-trees because there is no fragmentation process like fragmentation we saw in the B-tree. There's nothing in LSM. But we will see how, like, when I go to the performance section, we will see how they compare in real world. This is all theoretical, what we have learned in LSM and B-trees. So again, so we ran, now we got some ideas on how the LSM tree works, and then running with dbbench, how does it look real time? There is this same ReadWrite workload which I mentioned before. We ran here with 1 billion rows, and we wanted to see over time, does it really degrade write performance, or how is my read performance behaving? So if you can see this write throughput depicted here, it started pretty high, and over time it got some write performance getting a bit lower, and that's when the compaction process happens. And that's the cause of basically compaction. If you see the latencies, it was lower because it was writing fast, and as soon as there is some background compaction happens, your LSM write latency goes up. Also, one point I missed, so we were looking at the write and the read performance with this. So we saw one thread write was actually doing 5.2 million ops. So this shows that it's pretty fast when doing the writes, and it's balanced. So 16 thread read did pretty much like 6.3 million, but the write performance was the key in this. It was pretty fast. So quick recap, we talked about B-trees, LSM, design choices as the KeyValue stores, depending on the application, how do they behave. And the third one is fractal trees. This is being commercialized by Percona in databases. It merges features from B-trees and LSM, both of them, and what happens is it uses buffers at each node. And what that does is it helps for faster writes. The concept is same as B-trees. It's just that they have adding buffers, as I'll show in this diagram. So each internal node contains a buffer, and whenever you want to insert a record, right, it will insert into the buffer, and that's it. Your application will, it will just return, and the buffer, it doesn't have to be at the very bottom. It will just write it, and that's it. But once the buffers are full, then it starts traversing through entire tree, like in B-tree case. And also in fractal trees, there are several leaf nodes which are grouped together to form a bigger IO, which helps for space amp. And they say that it's sequential in nature when you have several leaf nodes grouped together. So we will see. In theory, write amplification is similar to LSM. It's better than B-tree and LSM in theory, but for leveled LSM case, it's similar for fractal tree. And then fractal trees are also suited for write intensive workloads. They tend to have lower write and space amplification than a B-tree, but we would see how do they actually compare when we test it out. Again, we saw how RocksDB was behaving for 1 billion rows, and then this is the TokuDB fractal tree. This is just showing like when your writer thread is running, okay, how is the IOs happening? Is it really stable, or there are a lot of ups and downs as you start filling up. And then there is read throughput here, the graph. So, and of course the write latency and read latency, they were basically dependent on the operations, how they were behaving. So it gets pretty like all these, ups and downs in the write latency graph. And that may impact your tail latency, like the outlier, how it may get bad for, if you have a out of my 100 like percentile latency, P99 or P90.99, it may get affected for Fractal Tree if you see these kind of not like a really uniform graph. But we will see how that looks. So performance comparisons, that's where we're going to look at. We discussed all these 3 different data stores one by one, and then how do they compare against each other. So again, this is based on a non-volatile media, P4500 SSD. We took 3 key-value stores: Wired Tiger, which represent the Btree, RocksDB for LSM, and then TokuDB, which represent the Fractal trees. And these are pretty latest versions we have mentioned here. So we got a data set of 200 million records, and we wanted to see how fast my read and write operations perform using these 3 different key-value stores. So we'll run the typical DB-bench workloads, ReadWrite. Again, I mentioned before, it's like 16 threads doing the reads, and then 1 thread is actually writing. So there is a lot of point queries happening in this workload. So it's a mixed kind of a read-dominated workload. And then overwrite, which is updating your keys in a random fashion. We'll see how that performs. So workload number 0 we've written is like the filling. Okay, I'm inserting my database, right? This is pretty important, right? With these 3 different key-value stores, I'm filling my database, and how much is my application writing versus how much is actually getting stored on the disk. And we are also looking at the IOStat level, which is happening on the device driver level. How many GB of data is actually written to the device. And then there is the right-hand column, which is SSD writes, including NAND. This is where we have performance counters on the flash, and so that's where it's actually garbage collection is happening, weird leveling, and all sorts of things. So we wanted to look at these different amplification at different levels. So space amplification is amount of disk space which is consumed relative to whatever my total operations was. So that's my first bucket here, app writes and disk usage, and I'm calculating my space amplification, where what my key value data store, how much is that total writes, like the size of my database, and what is if you look at my disk, if it's mounted, and if you do df-h or to look at what is my disk usage. So we see that in the Wired Tiger, which is a Btree based, it has 1.17 space amplification factor, which is higher than RocksDB and TokuDB, and it corresponds to some fragmentation which is inherent inside the Btree. There is write amplification per IOStat, where we are actually looking at the device level. Okay, how many write operations happened on the device when my application was filling. And then there is so in that case, pretty much everything, like for Wired Tiger and RocksDB, they were 1.07, 1.1, not much difference. And this is based on a 200 gigs of data set, and we We didn't do the filling the drive to 100% capacity or 80%. Maybe in that case you would see more, how does it behave over time when you have your device capacity much more filled. But in the case of SSD write including NAND, you would see that for TokuDB, there was a lot of write amplification when it's actually garbage collecting and it's looking at freeing up some blocks in the background, how my flash is behaving. We saw a lot of amplification for TokuDB case. So those were write amplification, space amplification metrics, but really how fast is my read and how fast is my write performance? Right here we have read while writing, 1 writer, 16 readers. So we see the top graph, which is showing ops per second. We look at RocksDB for the write throughput, and it's pretty fast compared to Btree or TokuDB. And in terms of read throughput, the Btree, it had best performance among the 3. And the P99, so that's also an important metric for your databases. How does that perform? So Fractal Tree, which is based on TokuDB, they had as high as 30 seconds of P99 write latency. So that was read write, and then we ran overwrite, which is updating your keys when you have a data set which is already written and you're trying to update some keys. We see that TokuDB and RocksDB both were pretty fast with that, but the Btree was performing lowest among all of these 3, and the P99 was bad for TokuDB. So there can be a question, okay, how much optimized my KeyValue stores were when we ran this? So we got there, basically we got the latest versions. For benchmarking case, we started with everything as baseline. So there was no optimizations for each set of KeyValue stores. All the configurations were pretty common, and that's how, if somebody would like to get started with these 3 key values, so that's the kind of performance levels you would see. But there are chances for optimizations for sure for all of these 3. So this gives you an idea, a baseline, how do they stand in terms of read and write performance. So we went through different data structures, how they compare against each other, and then the key takeaways. That would pretty much, the key value stores, they're important for unstructured data. The choice of my SSD backed key value store is definitely workload dependent. There is these factors which we covered: write amplification, space amplification, and there's a decision factor based on, okay, how much performance I want versus how much space you would consume for each key value store. So, and we looked at the traditional Btree case where it's great for read intensive workloads. It has better write amplification compared to the other 2 we saw. It suffers from fragmentation, which causes space amplification in terms of Btree. And LSM and Fractal trees, they are well suited for the write intensive workloads, as we saw in the performance. And then there is space amplification, which was better than the Btree case for LSM and Fractal trees. So yeah, if these were pretty much some practice we used, and basically what we conclude is, okay, if you have your workload, whatever is the demand of your application, is it a read intensive or a write intensive? Depending on that, you would choose different key value stores, and there's an important space and read and write amplifications. you should look for in choosing those key value stores. I think that ends our talk on the key value stores. Any questions, or if you want to reach me via email, I'll mention it here. Thank you. Yeah.
I was a little bit confused about the space amplification. I know with write amplification, then if you write 1 byte, then if you've got a write amplification of 3, then it writes 3 bytes to the disk. I'm guessing read amplification, if you read 1 byte, then it ends up causing 3 bytes of read.
Absolutely. For each operation.
Yeah, but space amplification, you write 1 byte, does that mean that it expands out to 3 bytes of space in the disk?
Yeah, we are looking at the disk level. How much amount of data get written?
Yeah, okay.
That's
When do you measure the space amplification? Right after the sequential fill or after the override?
good question. So we measured it during the fill, and like when it was inserting the data, when it was.
Which means in this fill workload, you insert each key exactly once, right? So this may not be a fair comparison between the Btree and the LSM tree, because you like run override workload. The LSM tree will have different versions of the same key in different levels.
Different levels. That's correct.
Right.
That's correct. We looked at running at override case as well, but like we couldn't finish that override case. But yeah, I agree with you. So there is a fill aspect when you have your 1 key per write, and then there is, you're updating it. So there are 2 aspects definitely considering.
Actually, in practice, I've seen a much higher space amplification than Btree. A little bit surprised by that.
Okay. It also depends on how much data you actually write. So have you seen on the flash, or that's all on the flash? Okay. Any other? Yeah.
So if you go back to the chart where you show the effects of compaction, one more. One thing I wanted to point out is that that's a log scale.
Right.
Reduction in throughput is really substantial. That's 2 orders of magnitude there.
Since there were a lot of data points and entries, yeah. But yeah, that's a good point. It's a logarithmic scale. Yeah.
Did you look at any KeyValue stores that use hash tables?
Yeah, there are some, but we did not in our experiments. But yeah, we actually were trying to use Aerospike. I think somebody came to us and said, yeah, that uses hash table, I think, Aerospike, and yeah, but we did not compare that. Yeah.
Can you go back to the test configuration slide?
Sure.
What's with the choice of dataset size?
What is the choice?
It's like 20x over provisioning, I think.
It's a 4 terabyte disk.
200 gigabyte dataset,
Mhm.
4 terabyte
Yes.
SSD. That's 20x over provisioning.
Over provisioning is
It means your SSD is not very busy.
that's
It
true.
means you
That's
just
true.
paid for 20 times the capacity, and so it works reasonably fast.
That's true.
Your numbers for write amplification, including the garbage
Mhm.
collector, reflect this fact,
Yes.
rather than say testing it at
Yeah, that's a.
capacity,
Mhm.
which would give you completely different numbers.
If you fill it full, or you can
80%
yes.
not full, but 80% plus whatever internal over provisioning you have.
That's I agree. these tests were done by like 200 million records, but if you have like, okay, 4 billion or 5 billion, you can over provision it more, and tendency of garbage collection would be a lot in that case. Yes. But this is like, okay, we ran this data set which is common for all three key value stores. Then you're comparing, okay, even if you don't want to fill to 80%, how are they performing at this level? But somebody would like to do, filling it more and seeing. Yep. Sure.
So in the record here, your key size and value size, are they uniformly the same size or are they just random size?
They are the same size, 16. You define it while running DB bench. What is my key and value?
So every record is has
Mhm.
a device key and byte.
Yep. Sure.
Google was like in the middle, kind of what you see data byte written and the write application. Seems the data byte is written is 3 times wide higher and write application is
Oh, so yeah, this write amplification is okay. Data bytes written on the device versus what my application did, which is the first column, right? So 190 gig. Yeah, so you are talking about TokuDB case here.
Compared more to the last column.
Okay. You are talking about this one, right? TalkDB with. Yeah. Yeah. It should be 3. Yeah. Okay. Yeah, that's actually outlier.
Isn't the 1.14 the first two columns compared against each other, the app rights versus the disk usage?
Yes. But this should be 605 divided by your app rights to get.
600.
Yeah. Yeah, this seem the values are fine. It's just the calculation. Okay, how are you computing? This should be 3 point something. So we'll correct it.
Yeah, you say over there it's for IOSTAT.
Yeah.
Yeah, where is the IOSTAT? That I'm not quite right.
Oh,
You got it from IOSTAT.
we looked IOSTAT and we also looked at proc disk stats.
There are versions of IOSTAT that won't report
Oh, really?
report the ratios correct.
Okay. So this is
But the bytes written is probably correct.
okay. I think that's it for our talk. Thank you. Yeah.